Hi, welcome to a video on one of the machine learning projects I've done. This is a machine learning project on quantum computing qubit pattern classification, where I was using a deep learning architecture known as long short-term memory recurrent neural networks. So, a couple quick disclaimers. Everything in the project is my personal opinion, doesn't represent the opinion of my employer, and this presentation does not constitute legal advice, even though I am talking about patents on it. So here's a look at my agenda for this presentation. This presentation is relatively quick. I'm going to dive into the project overview and goal. I'll talk about how I selected a data set for this project. I'll give my project plan. I'll show some of my exploratory data analysis. I'll show some of my results. And I'll talk about classification accuracy impact from a part of my data set known as patent family members. And then I'll have my conclusion. So, as an overview, patent offices around the world issue millions of patents every year. And individual inventors have received these patents as well as companies. And it's difficult for companies with large patent portfolios to understand and manage their patent assets for a specific technology area. Typically, that's a human-centric task where human beings are entirely handling the management of the patent portfolios. Well, with the rapid popularity of machine learning, it'd be interesting to use machine learning to help automate those tasks that are currently being entirely handled by legal staff. So this project is an attempt to demonstrate the ability of machine learning to classify patents as belonging in a particular category of asset. In this case, whether a patent is related to quantum computing qubit technology or not. And I rely on patent metadata information, the patent title, the patent's publication date, the serial number for the patent, the family identifier. While more accurate results would be achievable using the full text and drawings of a full patent document, that would require significantly more processing power. And so I wanted to keep this to a really fast and efficient process. All right, so let's take a talk deeper into what I'm talking about when I talk about using machine learning and deep learning. So machine learning, which uses statistical models and algorithms to make predictions, includes several different subcategories: supervised learning, unsupervised learning, reinforcement learning, deep learning, which I'm going to be using, and other techniques. Deep learning, which uses artificial neural networks to make predictions, includes things like feed-forward neural networks, convolutional neural networks, recurrent neural networks, generative adversarial networks, multi-layer perceptrons, and other techniques. And I'm using recurrent neural networks because they're applicable to text analysis. Long short-term memory, bidirectional LSTM, and gated recurrent units are specific types of RNNs that I chose to use in my project. So what is long-term short memory? I mentioned it's an RNN. Well, it's actually a solution to the vanishing gradient problem that RNNs suffer from. So recurrent neural networks suffer from short-term memory. If a sequence is long enough, whether it's text or something else, the RNN has a hard time carrying information from earlier time steps to later time steps in the process. RNNs rely on something known as backpropagation to modify the weights of the neural network. And this vanishing gradient problem is where the gradients that are used to update the neural network weight during backpropagation finally get smaller as they backpropagate through time. And if the gradient becomes too small, then the gradient isn't going to contribute much at all to learning. And so your earliest layers, who are near the end of the gradient coming back, are typically going to be the most affected by this vanishing gradient problem, which leads to the short-term memory where essentially the earliest layers don't learn as much as they could. So LSTMs, bidirectional LSTMs, and gated recurrent units are solutions to the short-term memory using gates to regulate the flow of information, basically allowing you to keep information for the long term so that you can make predictions on the best available data. So my goal is to analyze patents using deep learning, using this LSTM architecture for analyzing sequential text information related to patents. Now, patents include the body of the patent document, specification text, which is a description of the invention, the claims text, which is a description of the property right, and the patent drawings, which is usually an illustration of the invention. And there's also patent metadata, which is a mix of textual and numeric data. Now, as I mentioned earlier, analyzing the body of patent documents requires significant processing capabilities that I didn't want to utilize in this project. So I decided to focus on patent metadata and for this, and I'm doing a binary classification problem, basically specifying whether qubits are present or not using LSTM, bidirectional LSTM, and gated recurrent units. So the next step, once I decided that's what I wanted to do, was to find a data set with labeled patent data that I could use for training data for my deep learning project. So I searched on Kaggle for patent data sets and didn't really find anything that looked appealing. I then checked several patent journals that included machine learning information. Still didn't find what I was looking for. Finally, a search engine result led me to a site, then led me to another site that had the GitHub site created by Steve Harris. And in his site, he had the classification gold standard data set, which had this quantum computing qubit data set that looked absolutely perfect. The data set was actually created by Tony Tripp, who was a speaker at a quantum computing meetup I ran about 5 years ago. Steve and Tony and a couple other people, David Charles and Nigel Switcher, published an article about the data set in Science Direct and World Patent Information. So let's talk about my problem description for binary classification. So this was actually generated as the data set. So qubit generation for quantum computing refers to patents that discuss the various means of generating qubits for use in a quantum mechanics-based computing system. So it's got a classification of positive or negative. Positive if it's based on qubits, and negative if it's not. So for the positive patent documents, its types of qubits included superconducting loops, topological, quantum dot-based, and ion trap methods. For negative patent documents, it'd be anything not related to the above topics in the positive area. So things like applications, algorithms, other auxiliary aspects of quantum computing that don't mention hardware components and hardware for other quantum phenomena, but not those specific ones I mentioned above related to qubits. So here's a look at what the data set actually looks like. Now, this is actually a 5,000 row data set, of which a little over 50% are negative members of the Boolean class, and the remainder are positive members of the Boolean class. So in this little sheet here, I'm showing you the first 10 rows of the data set, which are those first 10 that list negative over on the classification. And then I grabbed like 8 or so from the middle of the document, which were positive. This is from like row 3054 on down. So if we look at it across the top of this table, it's really only 5 columns. The class, because again, class was labeled by humans. This is not something that is normally part of patent metadata. This is something Tony Tripp and the others he was working with did. Then you've got the family ID. The patent family ID or DocDB family ID relates to identifying related patent applications. Then there's a serial number, which is the specific number of this particular patent document. Then we have our title of the patent document. Then we have our publication dates for the particular patent documents. Now, let's talk about family ID for a moment. So family ID is used for identify all the related documents for a particular patent family. So if we look at these first 10 rows, they all have the same family ID. So all of them are the same patent family. And in fact, if I was looking at the full database, I think there's 17 members of this family ID in the full data set. Now, if you look at serial numbers, all the serial numbers are different because these are different documents. And actually, the first 2 or 3 letters will tell you where it came from. So, for example, you can see these are different country names, Canada, Australia, and so on, Germany, Denmark, the European Patent Office, Spain. Look down at the positive documents. That's actually a whole bunch of U.S. patents are listed down there. So you can see the different countries and the different numbers. If you look over publication dates, some of the dates are similar. Some of them are very different. That generally if a date is very different, it's probably because one document is a continuation of another document. So, for example, if we look at these first two Canadian documents, detection of electromagnetic fields, one of them's got a date in 1995, the other's a date in 2008. The 2008 document's almost certainly a continuation of the 1995 document. So that gives you a basic idea of what the data set is. All right, so let's kind of go a little bit further. So here's my deep learning project plan. I'm going to load the data set. I'm using Jupyter Notebooks. So we're just going to load the data. We'll do exploratory data analysis. We'll do data preprocessing and cleansing. Then I will use the Keras API to embed words for my patent title vocabulary tokenization. Because basically most of my analysis is going to be focused on the patent titles. Remember, the patent titles are saying things like detection of electromagnetic fields or quantum dot photon turnstile device. And basically, I'm hoping that my machine learning algorithm is going to focus in on the words that are most relevant to the particular title, the goal, in this case, identifying qubits, and determine that, yeah, quantum dot photons, that sounds like hardware for quantum computer. Quantum subflux quantum generator sounds like hardware for quantum computer, whereas detection of electromagnetic fields probably isn't quantum computer. So that's the kind of analysis that I want my machine learning to do. So well, the first thing we got to do is we got to embed all the words, and I'm using the Keras API. Then I create my LSTM, bidirectional LSTM, and GRU models. And I'm actually going to have these three models compete against each other to see which does best on on this classification problem. So as part of that, what I do is I've split my data set. Those 5,000 rows, I split them 80-20. So 4,000 of the rows are training, and the last 1,000 rows I'm going to use as test. Um, then what I do is I train my models, and I determine validation accuracy for the models. Once I've determined my validation accuracies for the models using the training data, I then take the best model and I evaluated it against the test data set. So I look at my results and then I did my analysis and conclusion. So here's a look at the exploratory data analysis I did on the data set. So if we look at it, and let's just take, for example, the first upper left chart here. So this is a distribution of title length. So the little bars are dealing with, how many characters are in each title. And then over on the left hand, that's the x-axis. And on the y-axis, we've got frequency. So the longer the bar, the more documents there are with that particular character count. So we can see immediately that if we look around, most of the character counts bars have pretty much been covered by the time we hit character count 150. So we'd say the 95th percentile of the data is probably somewhere around 150. Most of the data is going to be character counts for titles lower than 150. The same thing when we look at words, which is the next chart over on the top, distribution of word count. If we go out to about 20 words, and that by then we've probably covered most of the documents in the data set. But you'll notice the long tail goes pretty far. Even though I probably covered 95% of the patent documents by the time I hit 20, there are some documents that go all the way out to 40 some words. Same thing with characters. We look back there, even though most of the documents have covered by the time we hit 150 characters, my long tail goes beyond 300 characters for a title. All right. Looking down at actually, let's look at the last chart here on the upper right. This is target class distribution. Again, I've got somewhere around 5,000 patents. I think it's 5,039. More than 2,500 are in the non-qubit related, but a significant amount, more than 2,000, but a little less than 2,500 are in the qubit related. So we got slightly more non-qubit patents, but it's pretty close. If we look down in the lower three charts, the lower left-hand corner, his title length distribution by target. So it's really the same as my character count above, except now we're splitting it by non-qubit versus qubit related. And we can see that if we look at my long tail here, we can see that around 150, between 100 and 150, we notice the non-qubit titles tend to be longer. And then, and correspondingly, if we look between 0 and 50, the qubit-related titles, there's more patents with qubit-related titles that have less than 50 characters. Similarly, if we look at words, the non-qubit related seem to have more words, and the qubit related titles seem to be a little shorter. All right, so and maybe that makes sense. Maybe when you're dealing with the qubit related hardware, you're saying some stuff like quantum computer for a title or qubit, or you're talking about how the qubits are functioning, as opposed to some of the non-qubit related hardware applications might be more complicated and the concepts they're trying to describe, so their titles end up being longer. All right. And then the last thing I did is I did a feature correlation metrics over here on the right side, where I looked at word count, title length, and target and correlated them across with a little heat map. All right, so let's talk about our results. So I ran the 3 different models, the LSTM, the bidirectional LSTM, and the gated recurrent units, and I've got solid lines representing training and dash lines representing validation accuracies. And I then also ran it from a model accuracy comparison, and then I also did the model loss comparison. And this is my x-axis is epochs, and my y-axis is accuracy for the first grid and loss for the second grid. So looking at this first comparison diagram, looking at model accuracy comparison, we can see that GRU training started out lagging behind LSTM and bidirectional LSTM. Now the bidirectional LSTM is a little hard to see because it's right under the red dash line, so it kind of looks purple. It's green and red combined here, or a little purple or brownish. And we can also see that all the validation accuracy started out a little higher than the others. Red kind of lagged the most, just like GRU training lagged for the solid line. But then bidirectional LSTM validation and the blue validation, LSTM validation started out higher. So LSTM ended up the best here on model accuracy. So we can see, but really these are all really close. If you look closely around, say, epoch 4, GRU is slightly behind bidirectional LSTM and LSTM, but they're really, really close together. Now let's look over at model loss comparison. Again, GRE had the highest model loss to begin with. LSTM was slightly better, and then bidirectional LSTM started out the best. And then bidirectional LSTM led all the way in epoch 2, was still ahead. Epoch 4 was getting close, and by epoch 6, it was really close. So all 3 of these are really, really close. If we look at epoch 4 for model 4 accuracy, then when we get to epoch 6 for model accuracy, they're all right about identical at the same point, and the loss is very, very close at model 6. So really, all 3 of these models do pretty well. Well, you might ask yourself this question: why are they all so close together? Well, I'll get into some of the reasons why, but one reason to keep in mind is we're talking about patent titles. So if I go back to my data set around patent titles for a minute, these patent titles are not that long. Detection of electromagnetic fields, according to signals of electromagnetic fields. This one title, method of forming quantum mechanical memory and computations, might be a little longer, but most of these titles are pretty short. So the true benefit of bidirectional LSTM or GRU may not be coming into play here. And so all 3 of these may be roughly the same in terms of how competitive the models are. All right, I decided to take another look at why. Well, let me talk about final test accuracy. My final test accuracy for the best model, which was LSTM in this case, bidirectional LSTM, was 0.9675. That's a very high accuracy. That's saying I'm getting 96.7% correct on my predictions as to what how the patent should be assigned, whether it should be positive or negative when I'm running my test set against the algorithm to predict what the result should be. So 96%, again, that's really high. So what if this number is being driven by something else? So I wanted to run the system and modify examine the algorithm, examine the data, and see if I can come up with why I'm getting so high of accuracy numbers. Again, it could be because my titles are short and it's an easy question. Writing patents is a very formal art. Those titles are written by attorneys who are trained to write the titles in a certain way. And it could be that it's relatively easy for my learning algorithm to understand this data set and come up with the right answer. But I still want to dig in a little bit further and see if I can come up with some explanatory information. So I decided to run the data set by reducing the size of my data set. And what I decided to do was remove the additional patent family documents. So in my data set of over 5,000 patent documents, there's actually something like 3654 documents that are additional patent documents. So I have like 1429 unique patent family documents. So if I just drop every family member after the first family member, that removes 3,654 patent documents from my data set, leaving me 1429. So I ran this 1429 subset of the full data through the model again, only making that one change. So no real changes to the model or my code other than reducing the data set size. So final test accuracy dropped significantly. It went to 82% instead of 96%. Or rounding up, it would be 83 versus 97%. Let's take a look at model accuracy comparison. GRU again lagged behind the other two. LSTM and bidirectional LSTM were pretty close together. But notice this diagram here on the left looks a bit different from that other diagram. They're not close together to roughly epoch 7. Whereas before we were close together at epoch 2. So it took the model a while to get up to higher accuracies, all three of the models, a while to get up to higher accuracies. And again, they didn't hit quite the heights of the previous model, 83% instead of 97%. We're rounding up. And if we look at the validation numbers were also, again, a bit behind the model accuracy comparisons. Whereas if we look up here, the validation numbers were really close to the model accuracy comparisons. So significant difference by taking a look by removing the additional patent family documents. And again, on model loss comparisons, took them to probably about epoch 7 to get somewhere close. And again, the model comparisons were nowhere near the loss comparisons for the training data, training versus validation. And again, if we look back in the previous diagram, validations were much closer to the loss, even though they were off by a bit. Okay, so that tells you there's something going on very significantly when we remove those additional patent family documents. So they are definitely contributing to accuracy. Now, maybe this is the way it should be, that more information gives us better results. Or it could be that the model has learned that once it has a rating for one member of the family, whether it's positive or negative for qubits, it just makes all additional members of the family qubit related or not, which is, I believe, what the human beings who labeled this data set did. I think if we went through the data set and we looked at it, we discover that every single family only has one rating, positive or negative. So it could be the model learned that and just it's using that in the first version to hit 97%. And in the second version, it doesn't have those additional 1.0 ratings, and therefore it ends up at 82%. So that was my first interpretation as to what might be going on. All remaining patent family members have to have the same classification as the first member that's looked at 1.0 accuracy. And since I'm splitting training and test, I may very well have members of the same family on both sides, and therefore it's relatively easy classification problem in those cases. And my data set is something like 70% additional patent family members, so that's like a 1.0 accuracy on 70% of the data set. So that could be what's going on. My probability of full data, is based off of, I'm getting 96.75 accuracy because I've got an accuracy of 1.0 for all the additional patent family members. Whereas when I did the probability of one patent document per family, it was just 82.87. Now, however, the numbers don't quite match up. Now, again, it could be margin of error and probabilities and things like that. That's why I couldn't make the math work. But an alternative explanation is the algorithm could be learning which vocabulary words are most important by analyzing different wording differences between patent family members, i.e., this is a big data idea, more data leads to better results. So let's go back and look at our patent titles again for a second. So if we look at this first patent title, where I have 10 members of the same family here, and again, were in the data set, there were like 17 members of this family. I just didn't want to show all 17 in this diagram. You'll notice that most of the patent titles here are detection of electromagnetic fields. But there's also a couple patent titles here in this family. They're called according to signals of electromagnetic fields. It could be that as part of the learning algorithm, the model is learning that the important words for this particular patent are electromagnetic fields, and that detection of and according to signals of are not that important. And so the weights are mostly going on electromagnetic fields, and the other words are being reduced in weight. And so this is actual learning that is going on, and it's valuable learning that's present when we have the full document data set. But when we drop all the duplicates, we lose that learning. And so it could be that there's a lot of value in having the full data set. Similarly, if we look down here between lines 3054 and 3057, I've got three titles that look to be identical: method of forming quantum mechanical memory and computation. And then I got this other title that says quantum system comprising computational elements consisting of, and it's got a bunch more words. And again, it could be saying, well, the most important word here from a weight perspective is quantum. And perhaps, it's looking at what's in the consisting of to determine if there's any other words there that match in. And so that's what it's doing. It's focusing in on what's the most important word in its weight. And if I had just kept the first word, I lose those small differences in the learning. So it could be that, what I've got going on here is leakage between additional patent members. It also could be there's a lot of learning going on by having the full data set. And I'm not entirely sure, and it would require more investigation to determine exactly what's going on and what's driving my very high accuracy rate of 96.75. So in conclusion, I'd like to give my thanks to the Tony Tripp, Steve Harris, and the team that created the classification gold standard for quantum computing. I hope more groups follow their lead in releasing labeled classification data sets of patent information. During this project, I learned a lot about how LSTM, bidirectional LSTM, and GRU process text information, specifically with regards to patent titles, but also in general. I was impressed with the accuracy rates for classifying patents based on title information. My initial accuracy rate of 96.75 was very impressive and higher than I expected. And this project really emphasized the value of fully understanding your data set and the relationships within your data set. So thanks for watching this video. Have a great day.